All right, this is a document taken from an actual project, and this is just section 25 pages for only gravity column design. So I want to walk you through it so that you guys know exactly what I'm talking about. It's actual calculations from for a project, and as you see here, if I may go to the last page, this is an actual column output. In your midterm, I'm going to give you an output very similar to this. This is why I won't walk you through this so that you can read the entire page, know exactly what you're looking for, and know the information provided there. As you see here, this is the output for a software. It's called PCA column. Here's the column size on the top left-hand side. It says here 18 by 18 inch. So it's going to be square column. It shows here the code, units, the run axis. I wouldn't really care about this. The bars is going to be A615, which means grade 60 most likely. And it shows here also number of bars. We have here 12 bars. And you see the way they're done. The reason that we called here by axle because you can have moment in the X direction, moment in the Y direction. For our business, it's going to be only moment in about the X direction. So you don't have to worry about this. If I go down here, just look for more information. Just the file saved as project number and some information here. Concrete strength, 4.5 KSI, yield strength for the reinforcing bars. Model of elasticity, you don't really need it, and also you don't need the same for the steel. You don't need any of these numbers, right? Ultimate strain 0.03, which you guys know about. This is nothing here new. Here is the cross section area. If you take here 18 by 18 is going to be 324. For the bars, as you see here, you have 12 number 8. Cross section area is going to be 9.48 square inches of the reinforcing bars. This is going to be AS. Steel ratio 2.93. So the software is going to calculate this out for you. So you know it's going to be more than 1%. You have moment of inertia about the X, about the Y, the clear cover, some fee factors. I guess this is going to be enough information. What I care about from this page, I would say, if I may mark it here, information I need out of here, give it this reinforcing, the amount of reinforcing, steel ratio, and cross section area of the column, and AS, total cross section area of the steel. Other important information from the data that I just put in was the 4.5 KSI and 60 KSI. What's really important after you model the column this way, and as you see here, I usually put A3 bars, is going to be one at each corner and then one in the mid distance, mid span, or middle of the column. And then we start to add here one at each corner to gain more strength. Let me also show you the interaction diagram. Now it looks different from the one that you guys used to see, because usually the one that you used to see doesn't have this side. It only shows one side. The reason because you can have positive moment or negative moment, which means moment can be having compression at the top, tension at the bottom, or compression at the bottom, tension at the top. This is why I have here two sides. But for you, you don't really care because you can just disregard this section of it. You can just cover this here, let's say in red. And say, don't worry about this side. It's just going to be working on this side. You understand that this is going to be here the compression side and it's going to be the tension side?
Yes.
And then you see here that there is a line on the top and this line. If you like, this line here, this is going to be for VPN when you have axial load with a small eccentricity. And this is going to be the point whenever that you have moment and no axial load. And this is going to be the tensile strength. This is going to be right here at this intersection, which means it's going to be right at this location. So again, this point here represents a section that works as a beam. And the balance point is going to be right here. You guys recall definition of balance point? Can someone remind me, please? What happened to the balance point?
The moment and the axial load are equal.
At the balance point, something about the strain. Anyone recalls anything about the strain? What happened?
The strain is at 0.0.
The strain in the concrete is 0.03, right? And the strain in the steel is going to be right at the 8 point. Please remember this. It's going to be in your midterm. It's going to be a question. If you cannot answer it, you're going to lose this point. So be sure that you know definition of this point. So this is going to be the standard interaction diagram that you guys worked on, but I'm going to show you here two folds of it, because moment again can be positive or negative. Now, if I give you, let's say, a combination of some axial load, let's say here, and some moment value is going to be here. Therefore, you say, well, in this case, this load combination is going to give you a safe, let's say a safe column, right? Because it's going to be within the envelope. But now we need to mark it on this. If you remember the previous homework I gave you, the last one, the column that I gave you here, interaction diagram, and I ask you a few questions. One of the questions is find out this point. The other question, find out this point here, which is the balance of point. Another one, find out the tensile strength of the column if there's no moment acting on it. You guys recall this problem?
Yes.
Okay, this is going to be there in the exam. But instead of giving you the other interaction diagram, I can give you something like this. Not exact reinforcing, not exact strength, not exact size. Let's give you something like this with some sheet. So the output is going to be very similar to this. You see, I have too many columns, right? I can pick any of these columns and just use it. This is exactly what I'm going to do. So I'm going to ask you some questions, and this is going to be 6 questions. Can you please open this homework and be sure that you really have 6 questions on this interaction diagram? Are they 6 or 5?
There's 6.
6. Okay, good. There can be 6 problems. Same as the homework. Now, in the homework, I asked you to mark it on this, right? So now you can print it and mark it, but in your exam with Proctoria, you cannot really print. But you're going to have a piece of paper that you can do schematic. You can do very rough drawing of this interaction diagram and then show the point. Show whether the point is going to be inside or outside. Does this make sense?
Yes.
Now, the exam itself is going to be read very similar to what you have in your homework. But in the homework, it says, mark it on the interaction diagram. Meaning, in this case, you need to draw the interaction diagram. But please, when you do the axis, vertical axis or horizontal axis, right? The X and Y axis, like the moment and axial load, please use an edge. Don't do freehand and try to do neat sketches as much as you can. Now, when you do that,
will it be possible to,
excuse me?
will it be possible to print the sheet?
No.
Okay.
Yeah. System won't let you print it. Proctoria wouldn't let you print it. That's what I mean by the system. So what you need to do in the pencil, just do the 2 axes you don't really need to show me the other side, right? Why would you show me this? I don't need this. Just want to see one side of the interaction diagram, and then you show the point where the point is going to happen. Now, when you do the balanced point, you need to do it by analysis. Now, Venus here is asking me a question. How did I find out this balanced point without doing any calculations? Just because I know that usually there's going to be like a king, small pinch right here, and this is where the balance point is going to happen. And just, between this point and between this point, this can be kind of critical zone for the interaction diagram between these 2 points. All right. So I need to give you here a column and ask you to do the design. Are you guys with me? Following?
Yep.
Yes.
So I'm going to give you here the load criteria, meaning dead load and life load. So I'm going to give you again dead load and life load. Give you tributary area for this column. How many square feet this column is supporting? Also, I'm going to give you the life load and number of floors. So for example, if I'm going to say here that this building or this column supports 10 floors and a roof, it means that you take the dead load for the floor multiplied by 10 and you take one roof, because usually in a building you're going to have like a typical floor, and then at the end you're going to have one roof. In this case, you take 10 times dead load for the floor plus 1 times dead load for the roof, and then you do the same thing for the life load. And of course, at the end you multiply this by the tributary area. Tributary area is going to be for each floor. This column here supports about, let's say, 900 square feet, 400 square feet, whatever number is going to be given to you. When you come here right above the footing, you can add all of these forces and then find out dead load in terms of axial and life load also in terms of axial on the column. If you take these two values, add them to each other, this is what we call here the service axial load demand. If you do the load factors, meaning that you do the 1.2 dead plus 1.6 live versus 1.4 dead load, this is what we call here the factored load. So in the problem, I'm going to be asking you to do the service and the ultimate, which means a factor. When it comes to the ultimate, you're going to be using it to design the column, to do the check here. But the service, you're going to be using it to design a footing which is supporting this column. So just imagine the same homework that you have done, but add to it that you're going to have a footing right below this column. Are you guys following? Yes? No?
Yes, I'm following.
All right.
Yes.
Yep.
Good. Let me show you here some slides so that we
You
know.
said the service.
I'm sorry, say it again.
Professor,
Yes.
you said the service loads will be used to design the footing, and then the other ones will be used to
Okay.
the
Yes,
column.
this is what I said. This is to design it, or to actually design just the size of it. Like what happened in the foundation design section that we covered.
Okay.
Okay. All right. And you see here a previous slide set that we worked on for the columns. Slide set number 11. And that was a section only of the interaction diagram that we used. And the balanced point is going to happen when you have the concrete stress or excuse me, strain is going to be at 0.03, and the C, the strain is going to be at the yield point, the 0.02. And we have good section here. We have the analysis for it in section C. So if you didn't do it before, now this is going to be the time because you're going to see it in the exam. Here's a balance condition by definition and all the analysis needed to solve the problem for the balanced condition. If you are not sure, please go back to the recording and you can watch the lecture again. Now, here's a question that I've been asked and I answered quickly. I said, how would you know that this is going to be the balance point? I'm going to say, look at this standard diagram. It's going to be like the maximum point here, right? Maximum point in terms of the moment with any given axial load. And you see here, when you have this pinch, or you have the diagram is kind of squeezed, this is going to be the balance point. At the balance point, you're going to have a strain in the tension steel of 0.02, and you know that the strain in the concrete at any of these points is going to be 0.03, which means the capacity point. So now we know how I was able to do this on the diagram, and also we know how to do it by analysis. I'm going to say, just go through this section again. You have 3 slides to be able to finish it, right? So be sure that you know, and you know how to do it. By the way, did you guys see the formula sheet?
Yes, the very top cuts off when you print it off, but it's nothing too bad.
You have the PDF version, right?
Yeah,
Okay.
because when you print it out, you know how sometimes some printers need a border to be able to print.
So you can reduce the border to 0, I guess.
Okay, it's fine.
Yeah.
Just saying.
Okay. All right, but if you are able to see it on the screen, this is going to be sufficient for now, because during the exam it's going to be like a picture very similar to the previous exam, right? So you're going to see it and it's going to stay there forever. So you don't really have to print it, and please don't print it. Don't use it in exam. You're going to have all the equations out there. Okay. I have a very good question here. What happened when I have some rebars in the middle? Because this example here does not show any rebars in the middle. You have just top and bottom rebars. So the rebar, which is going to be in the middle, if I start here to put some rebars, as you know, at the bottom, I'm going to have a strain of this much. In the top, I'm going to have a strain of this much. If I'm going to put here another layer of rebars, right? If I put some rebars here and there, right? So let's say I'm going to put a circle here, right? Here's one rebar, here's another rebar. I guess I should be able to find out the strain in this rebar, can't I? Based on the location and the strain gradient, it is going to be an easy task for me to find out the amount of strain here based on this location, right? Once you have the strain, you can figure out if this is going to be compression or tension. So for example, I'm going to be looking here at this picture. Is this a strain in this rebar? Is it compression or tension here?
Compression.
Compression. Why? Because it happened right above the neutral axis. This is going to be the tension zone. It's going to be compression zone. Now I know how much compression is going to be in this steel. Compression in the steel is going to be equal to the strain multiplied by 29,000 KSI multiplied by AS. And with that, I'm going to have a new force that I'm going to put here. And I know the location of the force. I'm going to have C1, C2, and C3. That's it. When you do summation of the force in the x direction, it's going to be equal to 0. You say C1 plus C2 plus C3 minus T is going to be equal to the external applied force, P.
Wouldn't it shift C upward though? Like make C shorter?
The location of this?
Yeah, if you were to add compressive steel, right?
Yeah, this is true when you treat it as a beam, but when you work on the balance point, you don't have any of that.
Okay.
At the balance point, the strain here is given. You cannot change it. And the strain here on the top is given. Right? This strain is 0.03. You cannot change it. It's not going to change when you add more reinforcing. The strain also at the bottom is not going to change if I add tons of reinforcing here. The strain in the steel, in the tension steel, is going to be 0.02. This is by definition, this is going to be at the balance point. Therefore, the strain at any location here for any reinforcing is going to be kind of fixed. It's not going to change when you add more rebars. So if I have another rebar here at this location, let's say in many columns we do it this way, and also I have another rebar here, I'm going to say the strain in all of these layers is going to be the same. It's going to be this much. The strain here is going to be this much. So I cannot really change the strain here if I'm going to be adding more reinforcing or take out some reinforcing. This is unlike when you do the FMN for a standard beam. It does work this way. You start adding here more compression, you are shifting the CB and neutral axis and the compression block there and all of that. But in this case, it's not going to happen because location of this neutral axis is fixed. It's going to be based on this 0.03 and 0.02 and the total depth of the beam. It is not really related to the amount of reinforcing that you add here.
Okay, so just change your values for C1 and C2 then, right?
Exactly. So C1, C2, you can have another C3, C4, C5, depends on how many layers of rebars that you're adding. So for example, this one's not going to be compression, right? This is going to be tension. This is going to be compression here. So for if I'm going to be adding here 3 rebars in the middle, going to have one more compression force here, and this is going to be a tension force right here, right? How much is this tension force? You take the strain in the steel, multiply by 29,000 KSI, multiply by AS. If you have a couple of rebars here, you just add them. This is going to be another tension force. You're going to have T1 and T2. And then you apply the same equations that you have used here, which means you apply the same summation of the force is going to be equal to 0, summation of the moment about some point is going to be equal to 0. And with that, you should be able to solve the problem. So in our case here, we have a third bar, right? I'm going to be talking about this case here. Let's say that you do it this way. You're going to have compression 1, compression 2 is going to be for the concrete compression. Compression 3, it may happen for this guy here. Now you have the time before the exam. My advice to you, take something like this, like the previous one that you have in your homework, a column like this, and redo it again a couple of times. Be sure that you know how to answer it. Okay? So I guess now we're done with the column problem. It's going to be in your midterm. Now let's work on the foundation. Now for the foundation design, now we're talking about the same column, which means now you have the surface load and then you have also the ultimate load. So we're going to do check on the bearing stress. Now you have the surface load by just adding dead load plus life load. The allowable stress or the allowed bearing pressure is going to be given to you. Let's say 4,000 psi pound per square foot. You have the total load, the footing size may be given to you. So you can figure out the actual stress below the footing compared to the allowable stress and be sure that it's okay. If it's okay, you say yes, it is safe or it's okay. The stress below the footing based on the given surface load when you compare to the allowable is good. After this, you need to design the footing, design the reinforcing, do one-way shear check, and do punching shear check, or whatever is needed from you. Sure that you guys have seen this before, right? Yeah, absolutely. It's all recorded. I'd expected that you guys gonna be reading this again and doing this problems. So this slide set, 63 pages or 63 slides, you really need to go through it and understand each little thing in there and be able to solve with it. You remember this combined footing?
Yes.
How to design for the tensile steel? This is giving the exam. How to do this trick, find out the moment. And I'm going to give you, of course, the strength for the concrete. Also, I'm going to give you the rebar size. Any questions now? Especially that also you have the punching check that you're going to be doing and the one-way shear check.
Is 30 inches a standard thickness for the footing?
Which one? Say it again, please.
Is 30 inches a standard thickness for the footing?
Yeah. Can be 24, it can be 26 inches, 28 inches. It depends on the size.
Professor, could you go to example 5, please?
Here in this slide set? Okay.
Yes.
Yes, absolutely. Yes.
So could you go to the solution of it?
Okay.
I think it's page 20. Yes, right there. So you have S equals BT squared over 6, and you chose 4 for your B and 10 for T.
Yes.
I thought it was the opposite. I'm just having a hard time understanding why it's like that.
Okay. All right. Good question. Now, this footing width is 4 feet, right?
Yeah.
So when you think about it in plan view, it looks like this. If I may draw it here, it is going to be like this in plan, correct? Right?
Yes.
This width here is 4 feet. And this length is going to be 10 feet. Which is this length here. Now, because of this unequal loading and the relative location to the center, which means this axis. So in plan view, I'm going to put the axis like this, right? Let's say here's the axis. One side here is going to be pressed more than this side, right? As if you are putting pressure on one side than the other side. Therefore, this is going to be the moment, and the moment applied around this axis, it's rotating about this axis, right? So this side is going to be seeing here more compression
Right.
than this side. Therefore, the section modulus or moment of inertia is going to be about this axis. This is going to be B and this is going to be H. Or this is going to be B and this is going to be T, if you like.
Got it. Thank you.
No problem. Any other questions? Now, so this is going to be like one problem. One big problem is going to include a column. It's going to include the footing. And then you're going to have 5 problems here, or 5 small problems. Each one's going to be a couple of points for true or false, which you can do it online easily. Some of these questions is about discussion on spiral column versus tight column. You guys recall this issue? Difference between spiral column, difference between and tight column.
Yes.
Phi factor, what is this based on? And what values do you expect? Right? And of course, you're going to have this sheet, and by now you should know it by heart. Do you guys remember the confinement of concrete? You remember anything about this confinement thing, or no?
Yeah, the spiral is more confined based, or
Yeah.
sorry,
So
the
what does the
circular column
confinement is
is more
doing to the
confined based.
concrete? Is it
Basically,
increasing,
like,
or I mean, is it bring it to be a better column or better concrete, or lower in quality? I mean, what does it do?
It increases axial load capacity for the column.
Okay, does it also increase the strength of the concrete? Or it does not?
no, the strength of the concrete's already set based on the mix design.
Okay,
To increase the strength.
does it increase the strength? Okay, I want you to look at this and tell me what does the confinement is doing to the concrete. Does it increase the strength of the concrete? Does it increase the attainable strain? How much strain that this column is going to be able to take, or this concrete is going to be able to take? Just to study this type of things. You're going to have here on it some true and false questions, you know? Let me think about other things that you can make points easily. Do you know the definition of the balance point of the column? I guess by now you should know it, right? I said at the beginning, it says Gabby in the exam. So you need to understand the meaning of it. Also, do you know what is increasing the punching shear strength and what's reducing it? What are the factors that's going to increase the punching shear? You're going to say, in this case, go to this foundation section and just go through the punching shear check and look at the equations. See what's happening there. What variables is going to be increasing, or what factors is going to be increasing the strength, what factors is going to be reducing it? And just be ready for the question. All right, do you have any questions for me? Anything about Proctoria? Be sure that after hour and 15 minutes that you stop working on your exam. Exactly, hour and 15 minutes, 75 minutes. You need to stop, start to scan. I give you here full 15 minutes for the scan. I don't want to repeat what happened last time. You have enough time. Once it comes to hour and 15, stop working, start to scan.
So I just want to make sure I have it straight. So we're designing a column and then designing the footing, and then there's 5 or 6 true or false statements.
Yeah.
Perfect. Thank you.
No problem.
And you said it'll be similar to homework 7, correct?
Yeah, for the column, yes. But also be sure that you understand the foundation design is going to be there, right? Be sure that you understand how to do the column loads, because it's going to be your job to determine the column load. It's not going to be given to you. I'll give you the load criteria very similar to the project.
Okay. And how many questions in total would be in the one big problem?
Okay, let's say it's going to be 9, or someone, and all of a sudden now you see 12, and you're in the exam, the actual exam. Would that make any difference?
Kind of.
How's it? Okay, it's going to be 9 problems.
Okay.
9 in the first one, but it wouldn't make any difference for you.
Okay.
It is going to be one single PDF. because you're going to have a chance to upload only one single PDF. Miguel, are you there?
Yeah.
I don't understand your question. Can you please explain? Would there be only one room
During
scan?
the exam, Proctorio makes you like room scan a couple
Oh,
times.
okay, the room scan.
Yeah.
No, but it's gonna be recording voice, picture, and the whole thing.
Okay.
So you don't have to worry about anyone sitting with you, but be sure that he does give you any information because Proctorio is watching your eyes and whatever you say and recording this out. So
Okay.
any other questions?
Could you answer Eddie's question about the submittal, please?
Yes, okay. So we're done with the exam. We're just talking about the submittal, right? Any other questions on the exam? Okay, I guess we're good. Everybody's good about the exam. You have enough information. Let me look here at the submitted question. It says here for submittal 5, I was having trouble finding out the effective depth of the footing because there's no depth dimension for it. I decided to use 2'6". What is the footing size first? What footing size did you come up with? Eddie? Hey, Eddie, are you there?
Yeah, I'm here. I'm just checking right now.
Give me a second. Okay, AD says that he's using 13 feet by 13 feet. I'm gonna say here 2'6" is okay. I don't see a problem with it. And did you solve for the reinforcing, Eddie? Did you check the punching check? Punching shear, yes. Did it pass punching shear? Punching shear is good, Eddie? Or not really? You didn't finish it yet.
Yeah, the punching shear, I
Okay.
passed it.
Okay,
That's what
because
fit-
everything
yeah,
is
that's what fit
passing,
in the
everything is
capacity.
passing, and you decide to reduce it, let's say by 3 inches, and it's still good, so you can reduce it a little bit.
Okay. I'll check about that then.
Yeah. Here's a question from Jorge for the interaction diagram. Would the load be factored? I'd like to hear from others. When you do interaction diagram, is it concrete design or this is like soil design on the column?
Concrete.
Is what? Concrete. Concrete design. So in concrete design, do we do service load or we do ultimate load?
Ultimate load.
Concrete ultimate factor. Yes, right. Okay. So the answer is yes. This is correct. Interaction diagram is going to be factor. The only thing that you do service load is going to be for the soil bearing pressure. That's it. But for the rebar design, it has to be factor load. If you do the reinforcing bars with the service load, it's going to be considered as wrong. Other question. Shear beam or shearing beam, will it be in the exam? I'm going to say for the footing. You may see it for the footing design itself. So it's going to be like beam shear. If you like to call it shearing beam or beam shear, yes, it's going to be the one-way shear. This is why I'm saying here, please, for this foundation design, be sure that you read it very carefully and do it a couple of times. No problem. Any more questions? It is your time here to ask me, right?
For the balance point and the added reinforcement, I just want to make sure I had the derivation correct. You said it was strain over 29,000 KSI times AS, correct?
Strain over what? Say it again, please.
29,000 KSI and then multiply that times AS.
Okay, you take the strain, you multiply it by 29,000. You don't divide it by, right?
So it's multiplied then at that point?
Yeah, I mean, you know the stress.
Okay.
Can you write for yourself? Write down the equation says E, which is a modulus, the 29,000 is going to be equal to the stress divided by the strain. Can you write it down, please? If you have a piece of paper and a pencil or a pen. So in this case, the stress equals to what? Is it the strain multiplied by 29,000 or divided by 29,000 in this case?
It'd be multiplied.
Multiplied. Okay, with that, you're going to have the stress. If you multiply the stress by the cross-section area of the steel, it's going to get you a force, right? The stress minus cross-section area is going to give you your tension force. And this is what you need to use.
Okay, perfect. Thank you.
All right, no problem. Any other questions? All right, I'll let you go. Go ahead, please, and sign out. Guys, have a good evening.